All right, this is APBC, Unit 6, Section 11. This is BC only. If you are an AB student, stop watching this video and skip to Unit 6, Section 14, because the next 3 sections of Unit 6 are BC only. All right, so this is integration by parts. Okay, so recall the product rule, right? So the product rule was that when we differentiate u times v, we get u dv plus v du. If we solve this expression, right, for u dv, right, if we subtract the v du over, we get d dx of uv equal, or minus v du equals my u dv. If I then integrate both sides, I get uv, because when I integrate and differentiate, they cancel, so I get uv minus the integral of v du equals the integral of u dv, and that is the formula for the integration by parts. So the integral of u dv equals uv minus the integral of v du. So this is what you're going to want to memorize for integration by parts, but where this rule comes from is just undoing the product rule that you learned for differentiation. So when we use integration by parts. So if your integrand has a product, especially a product of two different types of functions, like e to the x times an x, or an x squared times a sine of x or something, and if that integrand does not work for u sub, it's likely parts. So slight differences in an integrand can make a huge difference in the method you use. So I want to walk you through two differences. So here we have an example of u sub. The integral of x times e to the x squared dx. See how my e to the x squared is inside a function, so I could make my u the x squared. My du would be a 2x dx. A multiple of that 2x appears in the integral. There's that x dx. So I can use u sub, right? I can use u sub, and I'll get that this integrates as 1/2 of e to the u du, which is a 1/2 e to the u plus c, or a 1/2 e to the x squared plus c. That's u sub. But if instead I gave you the integral of x squared times e to the x, minor differences, right? In fact, the only real difference is that here the x was at the bottom and the x squared was up at the top, and here those are switched. This is a product, but it's not u sub, because if I try to make u the inside of the function, it'll just be x. And u equals x is really never ever helpful, except occasionally in the case of arc trig. So basically I get the same integrand. If I try making u x squared, then it's problematic because it doesn't simplify e to the x in any way. So basically this problem's going to require parts. So steps for parts, right? First thing you're going to do is you're going to choose your u by using LIAT. LIAT stands for logs, inverse trig, algebraic, trig, and exponential. You choose u in that order. So if there's a log, you choose the log as u. If there's an inverse trig, so you go in that order. Whatever you didn't choose as u is your dv, and then you follow the parts pattern that the integral of u dv equals uv minus the integral of v du. So we're going to walk through some examples of parts. Okay, so remember we choose our u using LIAT, right? There are no logs, there's no inverse trig, there is something algebraic, and there's also something exponential. So I'm going to choose the algebraic thing as my u. So my u is going to be 3x, and everything that remains has to be my dv. That includes the dx, right? So u dv. I'm going to find du by differentiating u, which will be a 3dx. I'm going to find v by integrating e to the x dx and getting e to the x. So what I'm going to do now, remember that my pattern is that the integral of u dv equals uv minus the integral of v du, right? So what that's going to look like is uv minus the integral of v du. So this is going to be u times v, so 3x times e to the x, minus the integral of v du. Well, that's just a 3 e to the x dx, which I can now integrate normally. Notice I didn't write my plus c yet, right? The reason I'm not writing my plus c yet is I'm not done integrating, right? So I'm going to get 3x e to the x, that's my uv, minus, when I integrate 3 e to the x dx, I just get a 3 e to the x, and now that I'm done integrating, I write my plus c. So that's how I integrate with parts. All right, let's try another one. Okay, so again, see how I have a product, and it won't help me to make ux because it's never helpful to make x. It won't help me to make u 2x because then it won't simplify the cosine. So I use LIAT to pick my u. I notice that I have an algebraic function and an exponential, or sorry, algebraic and trig, my bad. It's been a long day. I have algebraic and trig, so my algebraic is my u. So this is u, and all of this is my dv. So u is 2x, which means du is a 2dx. dv is a cosine of x dx. When you integrate cosine, you get sine. Again, this is why it's important to remember the antiderivative rules. All right, so uv, right, so this is going to be 2x sine x, because that's my uv, right, minus the integral of v du is going to be a 2 sine x dx. Well, when I integrate sine, I get negative cosine. So I'm going to get that this whole thing, I'm just going to clearly separate this work, this whole thing is a 2x sine x minus 2 times this negative cosine of x plus c, which I'm going to clean up to make a 2x sine x plus 2 cosine x plus c. And that's it. All right. So sometimes a problem is going to require multiple rounds of parts. So let's walk through this, and we're going to learn a shortcut for this in a minute, but we don't know it yet, so we're going to walk through it the long way. So I'm going to use Liat to pick my u, right? So I notice that I have an algebraic function and a trig function, so my u has to be the algebraic function. So this is my u, and all of this is my dv. So u is going to be x squared, which means my du is a 2x dx. My dv is a sine of 3x dx. Now, here's where we're talking about that u sub and having and the comprehension that u sub of a really simple nature probably doesn't have to be written down. When I derive sine of 3x, I would have to multiply by 3 every time because of the chain rule. So when I integrate a sine of 3x, I'm going to have to divide by 3. So I'm going to get that this is a negative 1/3 cosine of 3x. And you can double check that by differentiating again to see that you get a sine of 3x. But again, the logic here is that with this really simple u sub, when I'm integrating the sine of 3x, I'm going to have to divide by 3 every time I integrate because it's the opposite of the chain rule. So now I'm going to do uv, right, which is going to be a negative x squared over 3 cosine of 3x. That's great, okay, minus the integral of v du, which are these guys. So that's going to be a negative 2/3 x cosine of 3x dx. Now, I would probably clean this up a little bit, but the issue at hand, just to keep in mind, is that no matter how much I clean it up, that second integral is still going to need parts again. So I would probably, I'd probably make the 2/3 positive because I have that option, right, because there's a minus a negative. So the issue is that this thing is also still parts, right, because this is a product. It's not going to help me. I have an x times a cosine of 3x. It's not going to help me to make either 3x or 2/3 x into a u. So I'm going to have another round of parts. So I have a new u, and I have a new dv. So when I do my new round of parts, my u is a 2/3 x. My du is a 2/3 dx. My dv is a cosine of 3x, which means that when I integrate, I'm going to have that 1/3 again, right? And it's going to be a sine of 3x. Sorry, there was a dx with that dv. So I'm going to get uv minus the integral of v du. So if we come down here, this whole thing, I still can't forget that negative x squared over 3 cosine. Oh, sorry, that was a cosine of 3x, my bad. Cosine of 3x, right? I can't forget that that's there, right? But now I get plus, because this was a plus in front, uv, which is going to be the 2/3 x times the 1/3 sine of 3x. So that's going to be a 2/9 x sine of 3x, right? That's my uv, minus the integral of these two. Well, that's going to be a 2/9 sine of 3x dx, and that's finally something I can integrate. So this is simple u sub. Now, when I say simple u sub, the logic here essentially is that I'm just integrating sine, but because it's a sine of 3x, I'm going to have to divide by 3. If you need to make the u 3x and your du a dx with a 3 in front, so you divide by 3, that's fine. It's up to you. It's also okay if you can just logic through that, but you are going to have to be able to figure it out. So I get negative x squared over 3 cosine of 3x plus 2/9 x sine of 3x. And then when I integrate this, again, I'm going to have to divide by 3. And when you integrate sine, you get negative cosine. So this is going to be a negative 2/27 times a negative cosine of 3x plus c. When I clean up the negative times a negative, my final answer is going to be a negative x squared over 3 cosine of 3x plus 2/9 sine of 3x plus 2/27 cosine of 3x plus c. And that is disgusting. Now we're going to learn a shortcut that makes that an awful lot easier soon. But let's walk through the hard way first. So go ahead and try P2. Remember, you're using Liat to choose your u, which means that your u is never the exponential, like because exponential is the last choice on the list. So, so my u is an x squared, which means my dv is the e to the 4x dx. du is a 2x. V is a 1/4 e to the 4x. Because again, when I integrate an e to the 4x, it's the opposite of chain rule. Instead of multiplying by 4 every time, I have to divide by 4. So I'm going to get that this is uv, which is going to be 1/4 x squared e to the 4x, right? That's my uv. And then v du is going to be a 1/2. So minus the integral of v du is going to be a 1/2 x e to the 4x, because it was 2/4, right? dx. So now, again, I'm going to need parts, right? So I'm going to do parts again, right? So my u is going to be the 1/2 x, which means my du is going to be a 1/2 dx. And my dv is going to be everything else, which is going to be an e to the 4x dx. So that means that when I integrate, I get a 1/4 e to the 4x. So now what's going to happen, notice that's a minus in front. So again, this was just like a separate work section. I'm going to get that this whole thing is equal to 1/4 x squared e to the 4x minus, and then in parentheses, uv is going to be these two as a product, right? So that's going to be 1/8 x e to the 4x minus the integral of v du. Well, that's going to be a 1/8 e to the 4x dx. So I'm going to go ahead and distribute that negative first, because otherwise I feel like it's going to get sloppy. So I get this 1/4 x squared e to the 4x minus a 1/8 x e to the 4x plus this integral. And this is just simple u sub. Again, you can make your u your 4x, or you could recognize that every time you integrate an e to the 4x, you're going to have to divide by 4. So what's going to end up happening is I'm going to get that this is 1/4 x squared e to the 4x minus 1/8 x e to the 4x plus 1/32 e to the 4x plus c. And again, disgusting, but slightly less disgusting than the last one, because e to the x is kind of friendly. All right, so sometimes your integrand won't look like a product at all. It'll just be a function, specifically a log or arc trig, that you can't integrate without using parts. When this happens, you're going to use Liat to choose your u. Well, log is right at the front. So this has to be my u, which means the only thing left, which in this case is just dx, is my dv. So u is the natural log of x, dv is just dx. du will be 1/x dx. And when I integrate to get v, it's just an x. So now this is going to be uv, which is x natural log of x, right? X natural log of x, minus the integral of v du. So minus the integral of a 1/x times an x times a dx. Well, that, if we just separate this a little bit as work, right, that's equal to an x natural log of x minus the integral of just dx. So this is x natural log of x minus x plus c. And that's it. Now, some people memorize that integral, and that's fine. I don't think it's awful to do by parts, but if you don't recognize that integrating just the simple natural log requires parts, it's going to create an issue. P3, arc trig, same idea. We use Liat, right? Well, arc trig's right here. It's pretty early in the list. So my u is the inverse sine, and my du is just dv. So u is going to be sine inverse. dv is just dx. So du is going to be 1/the square root of 1 minus x squared dx. And my v is just an x. So it's going to be these two multiplied together. So uv, which will be x times the inverse sine of x, minus the integral of these two multiplied together. Well, that's an x over the square root of 1 minus x squared, and that works for u sub, right? So if we look at this, if my u were a 1 minus x squared, my du would be a negative 2x dx, meaning I can cancel that x. So this piece, right, this piece, just this chunk right here, right, ends up being, there's a negative in front, right, but I'm not going to worry about that right now. So there's a minus sitting in front. But this integral ends up being x over root u times a du over a negative 2x. The x's cancel, So I get that this is a negative 1/2, the integral of u to the negative 1/2 du. So let's go ahead and clean that up a little, right? So if I plug that back into where we were, right, if we go back up to this, the negative 1/2 with the negative would become positive. So I get that this thing is an x sine inverse of x plus a 1/2, and then this becomes a u to the 3/2, right? So this is going to become a u to the positive 1/2 times 2, because it would be divided by a half. So I'm going to get that this is a 2 u to the 1/2, which was this thing, to the 1/2, plus c. We can clean that up a little bit, and it's going to look like this. So sorry, that was the work right there. So I end up getting that this is x sine inverse of x plus the square root of 1 minus x squared plus c. All right, so there's an awesome parts shortcut. So there's this epic shortcut for parts, but the caveat to this shortcut, right, the requirement, is that whatever u you're choosing derives to 0 eventually. So basically, u has to be x to the n, where n is greater than or equal to 1, and n is an integer. Can't be so not only is n greater than or equal to 1, but n is an integer greater than or equal to 1. So here's how the shortcut works. You're still going to choose your u using Liat, and when you do that, you realize that your u is definitely x squared. Since x squared eventually derives to 0, right? And I usually say that as the phrase derives away, right? It derives away to 0. It just disappears. What we're going to do is we're going to have a column for differentiating, which is going to be x squared. And we're going to differentiate that until it's gone. So 2x, and then 2, and then gone. We're going to have the other stuff, my e to the 4x, and I don't need the dx, I'm just going to use the e to the 4x. We're going to have e to the 4x, and we're going to integrate. So each time I integrate an e to the 4x, I'm going to have to divide by 4, right? Because that's the opposite of the chain rule, essentially. So I'm going to get a 1/4 e to the 4x, I'm going to get a 1/16 e to the 4x, and I'm going to get a 1/32 e to the 4x. And notice I go until they're level. I'm level with that 0. Then what's going to happen, right? So you can see that those are my 2 instructions, right? Make a first column for deriving, right, which I use d, and I derive all the u's. Make a column for integrating, which I called I, and I integrate. Once I've done that, I'm going to draw diagonal arrows. So let's just pick a color. So I'm going to draw diagonal arrows like this. Okay. And those arrows are going to alternate plus, minus, plus. And they keep alternating, plus, minus, plus, as many as you need. So I'm going to get that this is an x squared times a 1/4 e to the 4x, right? But it's going to be positive. Minus, right? That's plus. Minus, so this is going to be a negative. 2/16 would be 1/8 x e to the 4x, right? And then plus, this would be 2/32, which is 1/16 e to the 4x, and then plus c. So if I add all of these things together, I'm going to get my answer. So I end up getting that this is an x squared over 4 e to the 4x minus a 1/8 x e to the 4x plus a 1/16 e to the 4x plus c, right? And that's the shortcut. Now, if we go back for a sec to P2, which is way back. Nope. Nope. There we go. Okay. Uh-oh, I got a 32nd somehow, and it shouldn't be a 32nd. We should double check that. What did I do that was crazy? I get a 32 here, and it's not supposed to be a 32. I think we did something crazy. Well, now we're going to have to figure that out, because the shortcut is usually much more reliable. So this checks out, and this checks out. Why am I getting a 16? Did I do something crazy? I didn't. Oh, I did. I did something crazy. I'm dividing by 4. That's a 64. Sorry, the shortcut is more reliable than, or I'm more reliable than the shortcut. Sorry, it's been a long day. I'm tired. When you do 16 times 4, you get 64, not 32. Oops. So anyway, so this should be a 32, which checks out with what we did in P2 way back. Same answer. So Good, good, good. Sorry, sometimes my brain is slow. All right, so that's our shortcut, and it's awesome. All right, so now we're going to integrate using the shortcut. So remember, we pick Liat for my u, right? Algebra comes before trig, so this is my u. Once I see my u derives away to 0, which x to the third will, I can totally use the shortcut. So x cubed, 3x squared, 6x, 6, and 0. When I integrate, I have a sine of 10x, right? So when we integrate sine, and again, if it helps you, sine, cosine, negative cosine, down is deriving, up is integrating, right? So I'm integrating sine, that's going to be a negative cosine. And because of this 10x, I'm going to have to divide by 10 every time I integrate. So I'm a negative cosine of 10x. When I integrate negative cosine, I go up to negative sine, right? So this is going to be negative 1 over 100 sine of 10x. When I integrate negative sine, I go up to regular cosine. So this is going to be a 1 over 1,000, right, of regular cosine of 10x, right? And then when I integrate one more time, at least I pick tens, right? 1, 2, 3, 4, right? I get regular sine. Okay, so that's crazy. But then if I take these, right, I draw my diagonal lines, right? That's a plus. That's going to be a minus. That's going to be a plus. That's going to be a minus. So my answer, as disgusting as this is going to be, see how it's a plus, but it's already got a negative in front. So the plus being in front doesn't change the sign of it, and it already had a negative. So I get a negative x cubed over 10 cosine of 10x. Now this is a minus, but there's already a minus, so together those will be a plus. So I get a 3x squared over 100 sine of 10x. Right, so this one's done, this one's done. These are all pluses, right? So I'm going to get a plus. And if you want to leave it as a, I would leave it honestly as a 6 over 1,000 because why? Why? It's just a terrible idea to clean it up. So 6 over 1,000 with that x and then a cosine of 10x, right? So this one's done, right? And then this is going to be a 6 over a 10,000 and it would have a negative in front. So minus 6 over 10,000. Again, I don't see a reason that you would cancel a 2 out of that. It's just miserable. And that's a sine of 10x. And then the last thing not to forget is that there's a plus c. And that's disgusting, but if you had to do it the regular way, you'd be miserable. So, all right. Same thing here, right? We're going to use Liat to choose our u. And here the algebraic thing comes before the exponential. So this is my u. So yet again, this is a perfect case for using the shortcut. So x cubed, 3x squared, 6x, 6, and 0. When I integrate, it's an e to the 2x. So every time I integrate, it's still going to be an e to the 2x, but I have to divide by 2, right? So divide by 2, divide by 2, divide by 2, divide by 2, right? Sorry, it's a 2x. And then if we switch colors for our arrows, right? So diagonals go this way, right? And it's plus, minus, plus, minus. So I get, when I clean this up, I'm going to get an x cubed over 2, e to the 2x, right? That one's done. Then this is going to be a minus, so that's a minus 3/4 x squared, e to the 2x, done. This is a plus. And again, if you want to leave it as 6x over 8, I don't care. If you want to make it a 3/4, that's also fine, but you run a risk, right? The more you simplify stuff, the more you run a risk. And then lastly, it's a minus 6 over 16, e to the 2x, and then plus c. The shortcut is awesome. All right, moving on. So one really common trick problem is involving two functions that loop. So that's usually e to the x in either sine or cosine, because we even make a list of the cosine and sine loop all the time, right? Like this is the cosine and sine loop, and e to the x always loops back to itself. So when you see this e to the x cosine of x, it is parts, but it's tricky. So what I'm going to do is I'm going to go ahead and call this a for answer. So my answer is a. It'll make some more sense in a second. So when I go to do parts, right, when I pick Liat, I see that trig is before the exponential because literally the exponential is never u, right? So my dv is going to be v to the x. So I'm going to get u is cosine, derivative of u is negative sine x dx, dv is e to the x dx, which means v is e to the x. So now when I do my uv minus v du, okay, I'm going to get, I'm going to get that this integral here, right, this a, is equal to e to the x cosine of x minus the integral of e to the x times negative sine x, but that'll become a minus times a negative, so it'll be positive, so e to the x sine x dx. Well, I'm going to have to do parts again because I still have a product. So when I go to do parts again, my e is never ever going to be u. So I'm going to get that u is sine x, which means du is cosine of x dx. I'm going to get dv is e to the x dx, which means my v is e to the x. And I'm going to do my uv minus v du again. So I still have this a equals, I have this e to the x cosine of x, plus, now I do uv, so that's e to the x sine of x, minus the integral of v du. Well, a thing has happened now. This thing right here, this is also a. If you go back up to the top, the integral of e to the x cosine x was a. So what's happening here is I can combine that to the other side. I can add that over. Because what I have here is a equals e to the x cosine of x plus e to the x sine of x minus a. Well, I add the a over, and I get 2 times the answer equals e to the x cosine of x plus e to the x sine of x. So I can solve for that integral by dividing by 2. So I'm going to get that the answer is e to the x cosine of x plus e to the x sine of x all over 2 plus some arbitrary constant, right? Because once I don't have an integral anymore, right? Once I don't have an integral anymore, I have to write a plus c. So as soon as I recognize that I'm never actually going to integrate a, like I never actually integrate a, I go ahead and write a plus c. You could arguably write your plus c up here at this stage because that's when I stopped writing it as an integral. All right, so you're going to go ahead and try a looping problem. It's the same gist, right? It's just going to take a couple rounds to loop back to where you started, right? So my u is sine, and my dv is the e to the x stuff. This one's slightly harder because of the 2x, but you'll survive. So, cool. So I get that my u is sine x, and my dv is cosine of x dx. dv is e to the 2x dx, which means my v is a 1/2 e to the 2x, right? So I'm going to get that this is, and I'm going to go ahead and call this the a for answer, right? So my answer is going to be uv, which is going to be sine times that 1/2 e to the 2x, so 1/2 sine x e to the 2x, right? Minus the integral of these two, which is a 1/2 e to the 2x cosine of x dx, right? And that's going to be parts again, right? That's going to be my parts again. Sorry, it doesn't always go away. All right, so where this is my u, and these guys together are my dv. So my u, excuse me, is going to be cosine of x, which means my du is going to be negative sine of x dx. And my dv is going to be this 1/2 e to the 2x dx, which means my v is a 1/4 e to the 2x. All right, so now we're going to go ahead and do that again. So I have that this answer is 1/2. I don't know why I wrote the e at the end. It makes me feel weird. That's not where I usually put it. So 1/2 e to the 2x sine of x, that feels much nicer, minus, when we multiply these, a 1/4 e to the 2x cosine of x, right? And then, so that minus goes in front of all of this, so it's minus the integral of these, which will be a negative 1/4 e to the 2x sine of x dx. Okay, so now let's clean up some stuff, because that is this integral but with some stuff in front of it. So I have this a equals a 1/2 e to the 2x sine x minus a 1/4 e to the 2x cosine of x. And then this is a minus times a minus times a minus, so it will come out negative. So I have a minus 1/4 the integral of e to the 2x sine x dx. Well, that's a, right? So this is a minus 1/4. This whole thing was a. So what ends up happening is I end up getting a plus that 1/4 a equals 1/2 e to the 2x sine of x minus 1/4 e to the 2x cosine of x plus some arbitrary constant, right? So this is a 5/4 a equals this entire monstrosity. So to solve for a, my answer, I'm going to multiply that entire monstrosity by 4/5. So I get 1/2 e to the 2x sine of x minus 1/4 e to the 2x cosine of x plus c. You can put the plus c on the inside or outside. The other way to write this, because 4/5 times an arbitrary constant is just a different arbitrary constant. So it doesn't matter if the 4/5 includes the c in the parentheses or doesn't, because Again, 4/5 times some random arbitrary constant is just a different random arbitrary constant. So you might also see it like this. They're also okay. Again, that's not something you could do with normal numbers, but it is a trick that you can do here because it stands for an arbitrary constant. Oh, it is worth noting, though, that like this C, so this C is not the same as this C. So two different versions of an arbitrary constant. So that's kind of relevant. All right, so this is a trick you can only pull because they're arbitrary constants. All right, so we're going to do a definite integration by parts. I'm going to make the same argument I've made in every video we've done so far. It makes the most sense to do this without bounds first, and then once you've done it, once you've integrated, then you can deal with the bounds. So I'm going to suggest that you don't even think about the bounds until you've integrated. So I know that I'm going to use Liat. So in this case, my log has to be my u, which means that this stuff has to be my dv. So my u is natural log of x, which means du is 1 over x dx. My dv has to be x dx, which means my v is an x squared over 2, right? So I'm going to get that this is u times v, which is x squared over 2 natural log of x, minus the integral. When I multiply these, the 1 over x and the x squared just become an x over 2 dx. So that's a 1/2, right? That's a 1/2 in front of an x. So I'm going to get x squared over 2 minus, since this is just a 1/2 x, I raise the power by 1. It becomes an x squared and divide by the power. So I get minus a 1/4 x squared. And again, technically there'd be a plus c. Notice you can combine these together, though, if you want, because they're both, sorry, I missed it. You can't combine them together. Somehow I accidentally forgot to write the natural log. That makes way more sense. Natural log of x, sorry, it's been a long day. All right, so this is what I'm going to evaluate, right? So I'm just going to go up here and I'm going to cheat and say, cool, so that's x squared over 2 natural log of x minus x squared over 4 evaluated from 1 to 2. So when I plug in, I'm going to get 4 halves natural log of 2 minus 4 over 4, right? Minus, when I plug in 1, I'm going to get 1/2 natural log of 1 minus 1/4. Well, natural log of 1 is a 0, so that's gone. So I get 2 natural log of 2 minus 1, right? And then this is going to end up being plus a 4th, so I get 2 natural log of 2 minus 3/4, and that's about as nice as my answer is going to get. Now I can check that, right? Because again, we should always, we should consider using our calculator check when we can. Now I'm actually going to be pretty lazy because this is a pretty straightforward function. So I'm going to go ahead and type math 9, and then I'm just going to put in x natural log of x, because that one actually seems easier to type in, oh, my bad, than it does to go and put it in my y1. So with respect to x, from 1 to, oh, my bad, to 2, right, and I'm hit enter. Oh, hang on, I missed a parenthesis somewhere. Oh, I missed a comma when I quit out, sorry, 1, 2, my bad, hit enter, okay? And then I'm going to type in and see what happens, and again, it's been a long day, so there's a chance that this is going to go south, but we'll try. Right, so I type that in, minus 3/4, right? That's what we had. Hey, we win. Okay, so last one, and then that's the end of this video. So when we integrate this, right, so I know that I use Liat to choose my u, and it's never ever the exponential, so it's going to be the 2x in this case. Interestingly enough, because it's a 2x, you could totally use the shortcut, right? And I would suggest that you do, right? So when I do my work, I would suggest that there's nothing wrong with doing this, using the shortcut, right? Because that's my u and that's my dv. So my derivative is going to be 2x and then a 2 and then a 0, right? And when I integrate, it's just going to be an e to the x every time, right? Because that's how e to the x works. So I'm going to get this one as a positive, this one as a negative. So I get that this is a 2x e to the x minus a 2 e to the x, and that was a lot faster than any other option. So I get 2x e to the x minus 2 e to the x, and we're going from 2 to 3. Right, so when I plug in 3, I'm going to get 6, sorry, ignore the x again, totally been mathing for several hours. So 6e to the 3rd minus 2e to the 3rd, right? And when I plug in the 2, I'm going to get 4e squared minus 2e squared. So I end up getting 4e cubed minus 2e squared, and that's about as good as I can get it, right? There's not much I can do there. You could factor something, but it doesn't help a lot. So, so again, I'm going to argue this is a pretty easy one to put in. So I'm going to go ahead and do math 9, right? 2x e to the x, right, comma, with respect to x from 2 to 3, close the parentheses and hit enter, right? And then we're going to go ahead and do 4 e to the third. And again, the odds seem pretty high that sooner or later I'm going to do one of these wrong. Although earlier I did divide 16 by 4 and get 32, and that was pretty painful. So, you know. All right. Hey, there we go. All right. And that is integration by parts.